Okay, Atul, we are live now.
Good afternoon, everyone. So it's my pleasure to introduce our today's speaker, Koustav Banerjee, who is completing his PhD at Research Institute for Symbolic Computations in Linz, Austria, under the supervision of Professor Peter Paule. I know Koustav since 2016. So he spent his summer of 2016 here at IIT Gandhinagar. He did a summer research internship project with me, which led to a paper. And it was a great thing to work on it jointly. So today he'll be giving a talk on inequalities for the modified Bessel function of the first kind and its consequences. Over to you, Koustav.
Thank you. So is it visible perfectly?
Yes, sir.
Yes. So am I perfectly audible now? Okay. So today my talk is about inequalities for the modified Bessel function of first kind and its consequences. So there is a hidden statement about something. So for a first kind of order is, of course, I consider order only of non-negative real numbers. And what is consequences means? Consequences means in number theory and combinatorics. So I would like to thank the organizers for giving me this beautiful platform and a kind invitation to speak in this seminar series that's topics in special functions and number theory. So I chose as a special function, as I've already seen in this seminar series, Professor Devika Banerjee and Professor Atul Dikshit's student Rahul Kumar talked about some generalizations of modified Bessel functions. And Professor Devika Banerjee entangled the Bessel function study with classical analytic number theory like Voronoi summation formula. So I chose this topic because on another aspect of studying of asymptotics or inequalities of modified Bessel functions and its entanglement with number theory and combinatorics. So I'll sketch my talk in several context. So first, I will give an introduction to asymptotics of a real valued function. So what is mean? And then I'll give a brief sketch of history of modified Bessel function of first kind, which I denote by I nu x, which is standard. And then I'll go to a different case, so the consequences part, that what is a number theoretic and combinatorial aspects. And then I'll trace back again to what is asymptotics of I nu x, which is already known in the literature, but I'll still state. And then what is an error term, starting from the asymptotics and based on the estimation on the error term, which is entitled as error estimation, and which finally led to the inequalities. And I'll describe again that why these inequalities are important in the number theoretic and combinatorial perspective in the end of the talk. So let's start with the asymptotics part. So what is an asymptotic for a real valued function? So we say that fx is a real valued function which is asymptotic to phi x if limit x tends to infinity, fx divided by phi x equal to 1. So it's mathematically, it says that as x grows bigger and bigger is large enough, fx and phi x has the same growth. But in other words, to me, it seems like if fx may be constituted of our familiar functions, but as a whole, fx is not to be well known. What I will explain in the next slide, what is not being well known or what we want to get asymptotic. So fx in terms of our familiar functions, in terms of phi x, such as exponential functions, logarithmic functions, trigonometric functions, polynomials, algebraic functions. So in short, we say that fx by the symbol asymptotic to phi x as x tends to infinity. And in short, I say that if f is asymptotic to phi, which is inevitably mean that fx is asymptotic to phi x, then you want to know the asymptotics of f in the following sense, the full length asymptotic expansion, what I say, that fx is asymptotic to f phi x times psi x. So what is phi x is like contributes the major term, and the psi x is like an error term, m from 0 to infinity, am divided by some chi of x to the m, where of course a0 equal to 1, because if we take limit x tends to infinity, fx over phi x as x tends to infinity, if a0 is 1, and then a1, am are sequences, and this chi x has to be an increasing function in x. So as x tends to infinity, it goes to 0. So then limit x tends to infinity, fx over phi x equal to 1. We trace back to the definition. And then am may depend on the parameters involved in f. we'll see in the Bessel functions example what I mean by may depend on the parameters involved in f. So going far, for an example, if I take fx to be gamma x, so x is a non-negative real number I take. So for fx to be a gamma x, where gamma x is defined to be this 0 to infinity to the minus tt to the x minus 1 dt, then due to Stirling's asymptotic formula, it is well known that gamma x is asymptotic to square root of 2 pi over x times x over e to the x, but times sum over m from 0 to infinity am divided by x to the m. So here fx is gamma x, phi x is square root of 2 pi over x times x over e to the x, and this some chi of x is x to the m. And then where am is given by this sequence is determined by this expression, this 1 over 2 to the m times m factorial, the 2mth order derivative of ddx of half of x squared divided by x minus log of 1 plus x to the power m plus half at x equals to 0. And if we see first few values, if we compute that a0 is 1, a1 is 1 over 12, a2 is 1 over 288, and so. So if we look closely, that a1, a2, the denominators of ai's are closely related to the Bernoulli numbers. So why do we need this kind of full stretch asymptotic expansion? So for a given fx, if I write fx divided by phi x minus psi n of x. So my psi x was some m from 0 to infinity am divided by chi x to the power m. So if I truncate at n, and then the rest, the difference of that is my error term from the truncation point of n plus 1, which I denoted by n of x. So what is the estimation of the remainder? So fx divided by phi x minus this sum m from 0 to n, am divided by chi x to the m, which is defined to be en of x, and the absolute value of that, which we want to bound by cn, some constant dependent on n, divided by chi x to the power n plus 1, which is equivalently say big O of 1 over chi x to the power n plus 1, the next term. So cn is again a constant, maybe depend on the parameters of the functions f. And now this inequality holds for all x greater or equal to x0. So I'll state that why for our purpose x0, to know x0 explicitly, and this cn to know explicitly cn is important. So let's move towards a brief history of modified. First, we're starting with the Bessel function, and then we'll come up with the modified Bessel function. So as early as 1694, John Bernoulli came up with the first order nonlinear differential equation of this form. This y prime means dy dx equal to x squared plus y squared in connection with the work on curves. But he couldn't able to solve it later, which was solved by the older brothers of the Bernoulli family, which is James Bernoulli. So James Bernoulli's idea was to introduce the variable y to be minus 1 over u du dx, and then he reduces this equation, first order nonlinear differential equation, y prime to be x squared plus y squared, to the second order differential equation is u d2u dx2 plus x squared u to be 0, and making an answer u from n from 0 to infinity a n x to the n. He obtained a solution y to be x cubed divided by 3 plus x to the power 7, 3 squared times 7, 2x to the power 11 divided by 3 cubed times 7 times 11. All these denominators is kind of factorials. So this was the first hint to get a certain kind of solutions for a differential equation that later that was presumed to be connected with the Bessel function, so, and which was settled, that which was confirmed by von Lommel, the mathematician. But later in early 18th century, the Italian mathematician Count Jacopo Riccati investigated those curves whose radii of curvatures are functions of their ordinates, and consequently led to a more general form of this differential equation y prime equal to x squared plus y squared. So this form y prime plus ax squared equal to by to the c. So if I take a equal to -1 and b equal to 1 and c equal to 2, then we lead to the differential equation. The a and b are constant and c is not necessarily an integer. Riccati moved forward to say, which says that Riccati's differential equation, which is of the form dy dx, where equal to p plus qy plus ry square, where all p, q, r are functions of x, but with assumption that p and r not identically 0. Again, if I take px to be x squared, qx to be 0, and rx to be 1, then we again trace back to its original form, what John Bernoulli came up. Now, later in 1724, Daniel Bernoulli studied again a particular type of this differential equation, because Riccati said that later to Daniel Bernoulli to study these differential equations of this form. Bernoulli considered this y prime equal to ax to the n plus by square. So if I take n equal to 2, a equal to 1 with respect to the John Bernoulli's case, and if I take px to be ax to the power n and q to be 0 and rx to be b. This later has a deep connection with the Bessel functions. After Daniel Bernoulli, Euler, Lagrange, Laplace, Poisson, among many others worked on this Bessel's equation, although I didn't define still what is the Bessel's equation. But almost 100 years later, Bessel came up with what we call the Bessel function. This is the first systematic study in a problem of a Kepler in context of the planetary perturbation. So what is the Bessel's equation? So Bessel's equation is x squared times d2y dx2 plus x dy dx plus x squared minus nu squared times y is 0. Nu to be a complex number, but we want to stick for this talk nu to be a non-negative real number. So if I let x to be I times x, then this modified Bessel's equations leads to x squared times d2y dx2 plus x dy dx minus x squared plus y squared times y equal to 0. So if we plot this Bessel, if we get the solutions, there are two solutions linearly independent, these Bessel functions. Those functions, if we plot in the graph, we see that they are oscillatory along the positive real axis. But for the modified Bessel functions, if we see the solutions of this differential equation, which has two linearly independent solutions, namely I nu x and k nu x. So I will talk only about I nu x today, which is called the modified Bessel function of the first kind, and k nu x is called the second kind. So for I nu x, the definition is m from 0 to infinity, 1 over m factorial times gamma m plus nu plus 1, x divided by 2 to the power 2m plus nu. So if my function fx to be this I nu of x, then we want to know how this function behaves. So I plot this in Mathematica and put the picture here, although this is very tilted, which is wrong, but I mean bad. But still, this I1 of x, I3 over 2 of x, I2 of x, I5 over 2 of x, and I3 of x. So these are exponentially growing. And for other cases, this is exponentially decay is there. So they are not oscillatory. So now, modified Bessel functions, as I have already stated, that it has a close, intimate connections with other portions appears in number theory, in analytic number theory, like Voronoi summation formula. It appears in formulas of Ramanujan's in context of zeta function, in sum of squares formulas, and which can be found in the works of Professor Bruce Bund, Professor Atul Dixit's works. But I will stick today to another perspective of studying these modified Bessel functions in study of some combinatorial problems to attack the combinatorial features of some sequences, which is called log concavity. So before going to that, what is the definition of log concavity? So a sequence alpha n is called log concave. If for n greater or equal to 1, this alpha square of n minus alpha of n minus 1 times alpha of n plus 1 is greater or equal to 0. And we say strictly log concave if it's strictly greater than 0. So in other words, if we look familiar, if I take this polynomial, 2-degree polynomial of binomial 2 choose k alpha of n minus 1 plus k times x to the k. So this polynomial is alpha of n minus 1 plus 2 alpha of n x plus alpha of n plus 1 x squared. And if I see the discriminant of this polynomial, it's exactly 4 times this object, this alpha square n minus alpha of n minus 1 times alpha of n plus 1. So in order to have the discriminant positive, we want to have the square root of this thing has to be positive. That means this polynomial has only real zeros. So I will define that I put it here that the polynomial to be j alpha to n of x. I will define why it's called j alpha in a moment. And before that, I'll say what is the higher order Turan inequality. A real sequence satisfies higher order Turan inequalities if for n greater or equal to 1. This 3-degree polynomial, this binomial 3 choose k alpha of n minus 1 plus k x to the k has only real zeros. Similarly, one can see. So why I put this j alpha 3 of n? So these log concavity higher order Turan inequality properties, this Jensen studied this type of polynomials so that one can extract out these features, log concavity higher order Turan inequality of this associated with a sequence alpha. degree D and with shift n. So I should write it here n minus 1. I do apologize for this notation, this notational mistake. This should be n minus 1 because this n minus 1 shift. So it comes from a Maclaurin coefficients of certain entire functions belongs to Laguerre-Polya class, which I will not discuss today. But Jensen studied these polynomials, and the real zeros of these polynomials encodes the higher order log concavity and higher order tyrannical more general of degree D polynomials whether they have the only real zeros or not. So let's go for an example to see that why this law, how this log concavity higher order Turan inequality property. So for partitions, I will take alpha n to be the Pn. Then what is the partition? Partition of a positive integer n is a weakly decreasing sequence of positive integers whose sum is n. Like P0 is defined to be 1. I chose P5 to be 7. So the partition function has a long history. It dates back to Euler, first systematic study due to Euler. It's the generating function for the partition. It's n from 0 to infinity, Pn q to the n. Just formally, it's an infinite product 1 over 1 minus q to the power n. So if I expand this thing 1 over 1 minus q times 1 over 1 minus q square and expand this thing and collect the coefficients of q to the n, I get Pn for each n. So today, partition function has several combinatorial features and it has nice congruence properties as we have seen that since Ramanujan. But today, since we talk about asymptotics, so we want to know the growth of Pn. So McMahon computed in 1916 this P of 200, this huge number. And 2 years later, Hardy and Ramanujan had a monumental breakthrough. They encode that Pn is asymptotic to 1 over 4n square root of 3 e to the power pi square root of 2n divided by 3 as n tends to infinity. So as n gets longer and longer, if I see this Pn, this grows like these exponential functions over 1 over n form. The story completed due to the work of Rademacher and Lemma during the time 1936 to 1939 in a series of papers. So they define mu n to be pi over 6 square root of 24n minus 1. This is quite similar to that pi square root of 2n divided by 3. And they denote, they obtain the expression Pn to be an infinite expression. It should be infinite, but I truncate it at here n, and then the remainder term R2 of nn, because Lemma obtained an upper bound for the absolute value of the R2 of nn, the air term. So in this expression, this akn is certain exponential sums closely related to the Koustav sums, and what you see here is a major term. And for R2 of nn, this is the air term. So after this Rademacher and Lemma's observation and this beautiful expression, the question is, what should we do? That in almost 70 years later, Professor William Y.C. Chen, in 2010 formal power series and algebraic combinatorics conference, he conjectured that Pn is for n greater or equal to 26 is log concave. And 5 years later after that, De Salvo and Igor Park proved this Pn is actually for all n greater or equal to 26 is log concave. So their proof sketch is based on that, on this Rademacher formula and this Lemma's bound, error bound. They took n equal to 2 and write Pn equal to Tn plus Rn as a remainder term, and they write it as Tn times 1 plus Rn over Tn. So Pn is a product of a major term Tn and 1 plus Rn over Tn, and then they took the log of Pn, so it is log of Tn plus log of 1 plus Rn over Tn, and then they prove that it's P square of n. So if I see this log concavity of alpha squared of n is strictly greater than alpha of n minus 1 times alpha of n plus 1. If I take log on both sides, and then we see that 2 log of alpha of n minus log of alpha of n minus 1 minus log of alpha of n plus 1 has to be greater than 0. So in this, yes?
Yeah, just a question. So yes. Is there any theoretical reasoning for greater than or equal to 26, or is it that it just comes up like that?
It's just come from the experiments that they took that p square of n divided by minus p of n minus 1 times p of n plus 1 is greater than 0. But it's still unknown. I thank you for your question. It's still not known that what is the combinatorial proof for Pn is log concave. If we do know the combinatorial proof explicitly, not analytic proof, but the combinatorial proof, then we can somehow get the idea of why this 26 appears.
Okay. Thanks.
And so Pn is for n greater or equal to 26 is log concave. So it somehow says that it's, if I say this according to this language, so if I say this jp2 of n, this polynomial has only real zeros associated with the pn. But Professor Bill Chen himself, along with his students Jia and Wang in 2019, moved further. They proved that Pn for n greater or equal to 95, again, this is certain constants, is 95, satisfies the higher order Turan inequality. So that means this, the Jensen polynomial associated with Pn with degree 3 and shift n is again has all real roots. So, and then Chen proposed a conjecture on this for general degree, but before to that, we move to a broader class of functions, which is called which I will refrain from talking about in details, but it's a modular form. It says that a function is a modular form of weight k on SL2Z. That means it's a nice function on a holomorphic function on the complex upper half plane, which has a certain nice properties. So in definition, it's f of a tau plus b over c tau plus d is c tau plus d to the k, some multiplied fact, and then f tau. So if k equal to 0, then this is a nice symmetry is there. So it's called modular function, and for modular form of weight k, where a, b, c, d is a matrix in SL2Z. That means determinant 1 and a, b, c, d all are integers, and with a pole of order m at infinity. Then we know that the Fourier expansion of f is given by of this form. F tau is starting from minus m plus positive integers a f of n. So as f varies, a f of n varies q to the n. M is a non-negative rational numbers, and a f of minus m is non-zero. That means it's ordered at m minus m, I mean, where q is e to the power 2 pi I tau, and tau is in upper half plane. So why I put this information? So if I see these partition functions, they are the Fourier coefficients of modular form, namely 1 over eta tau q to the power minus 1 over 24 times n from 0 to infinity pn q to the n, where eta tau is this q to the power 1 over 24 times this infinite product 1 minus q to the power n, but mod q, of course, less than 1 on the unit disk is a Dedekind eta function. Dedekind discovered in 1877. So Pn, actually, we can write it in this notation. Pn is af of n minus 1 over 24 for n f equal to 1 over eta. So as f varies, we can get this. We can get some more nice of Fourier coefficients, which has certain number theoretic very good features. So in 2019, Michael Griffin, Ken Ono, Larry Rowland, and Don Zaki proved that if f is a modular form of weight k on SL2Z, then for any fixed d greater or equal to 1, the Jensen polynomial associated with the Fourier coefficients, this af with degree d and shift n, are all hyperbolic for all sufficiently large n. Sorry. So what do you mean hyperbolic? This is called that the Jensen polynomials are all have real zeros. This is the definition of hyperbolic. So now we trace back to the conjecture of Chen, Jia, and Wang. They conjectured that for every d integer greater or equal to 1, there exists an integer nd such that jpdn of x is hyperbolic for all n greater or equal to nd. So Griffin, Ono, Rowland, and Zakia says for all sufficiently large n. So they do not know what is the cutoff for nd. They say for all sufficiently large n. But immediately after their paper, Larson and Wagner published that jpd of n, this polynomial, is hyperbolic for all n greater or equal to nd, with a condition that nd has to be less than 3d to the power 24d times 50d to the power 3d square, which is bounded by a super exponential d to the power d square. But in the paper of Griffin, Ono, Rowland, and Zagia, they experimented, and they suggest that nd cannot be more than a polynomial growth. Nd has to be approximately of the form 10d square of log d. So if I say, so what is nd? Nd, if I take n2 is jp2 of n, which is log concave. That means n2 will be 26. n3, the higher Turan inequality, is 95. But they say it's of the form bounded by d to the power d square form. So it's still, we do not know that how one could prove this nd has to be of this form 10d square of log d. So we move further to a more general class of functions. I say functions because they're holomorphic functions on the unit disk. So we define that it's a m from 1 to r. This is a certain object, q to the power m divided by 24, n from 1 to infinity, 1 minus q to the m n times script to the power delta m. Delta m is integers, which is defined to be q to the power minus n0. N0 is defined by this delta m and this r, and sum from n from 0 to infinity. Coefficients are denoted by dn, q to the n. One can see this formally, or otherwise one can see in sense that this is actually a Dedekind eta quotients. If I take delta m to be minus 1 and r equal to 1, then I got the q to the power minus 1 over 24, n from 1 to infinity, 1 over 1 minus q to the power n. Then this n0 will be 1 over 24 and dn will be pn, as we have seen earlier. So to this object, I associate another two parameters that delta 1 is defined to be minus half of some m from 1 to r, it's delta m, and delta 3 of k is defined to be this minus of some m from 1 to r, delta m, GCD of m of k squared divided by m. So I do not need any other properties because, so in the style of Hardy, Ramanujan, and Rademacher, Ethan Sussman in 2017 got this kind of expression, this infinite expression for dn, when delta 1, this delta 1 is either a half integer or an integer, because delta m are all integers. And with this condition, then dn is given of this expression, infinite expression, and where this script akn is I didn't still define, and this I of 1 plus delta 1. So delta 1 is positive. That means I of 1 plus delta 1 will be of the form either, and this Bessel function will be of the form either integral order or half integral order, of course positive. And script akn is like exponential sums. For other parameter, if I take delta 1 is less or equal to 0, into 2 years later, Shen-Chan obtained this expression dn to be an error term, which I didn't define. And then again, script akn to be exponential sums, and then it's minus 1 minus delta 1. So if delta 1 equal to 0, then it is at most minus 1, or if delta 1 is higher, minus 1 is then it is positive. Minus 1 minus delta 1 is again positive. So this is why we in this talk I will talk about only modified Bessel functions of first kind of integral order, positive integral order, or half integral order. So in order to know, I say it's mode about. What is the mode about means? It's we want to know the combinatorial properties, that is log concavity, higher order trivial inequality of certain sequences of dn. Then we need to estimate I nu x for a nu to be half integral and Koustav-like sums or exponential sums. So I came up with this dn to be a cubic partitions in my PhD work, and then where the Bessel functions appear of order 2. But Bessel functions of fractional order has a closed form, but for order 2, I didn't have a closed form. So I want to get a asymptotic expansion, and I want to get an explicit error bound from that asymptotic expansion in my context. So during my work, I asked Professor Paule that what should one do with this? And then when Professor Paule, when I hear from him that he said it's a classical function, and if one could study in its full generality what in your purpose, then it would be a wonderful idea to carry on this project. In the meantime, I saw that if I see that dn equal to pkn, so it's pkn is a k colored partition. If I don't go into the combinatorial application, it's just the generating function is that n from 1 to infinity, 1 over 1 minus q to the n to the power k is some n from 0 to infinity pkn of q to the n. So if k equal to 1, then this is a partition function, which says that it's a how many ways one can write n as a sum of non-negative integers, positive integers using k colors. But one can also input k either not by discrete but any continuous parameter alpha, but it's no longer then has these combinatorial implications or features, but it still has a nice formula due to an instance of Nekrasov and Okunkov formula on the hook length in their study of, I think, supersymmetric Gauss theory from physical phenomena. So in last year in November 2020, Professor Catherine Brinkman, Ben Ken, Larry Rowland, and Jack Tripp proved the log concavity of this function pkn for k greater or equal to 2 integer, which was actually conjectured by Chan, Fu, and Tang in 2 years earlier. And for P alpha n, if I take K to be an alpha, a continuous parameter, then this was the law concavity of P alpha n was conjectured by Bernard-Heim and Neuhauser. But in order to prove this conjecture, the key fact was in the estimation of the modified Bessel function of the first kind of order greater or equal to 2. So in the paper, they say that in order to make the exact formula in theorem 2.1 means the theorem for their law concavity of Pkn or P alpha n useful for our purposes, we need strong estimates on the Bessel functions. Although many Bessel function estimates are standard and a whole asymptotic expansion is known, we are unable to find existing bounds suitable for our purposes. I did a search, but I couldn't find in detail such a result. But as I was new in this domain, so I had to rely on their comment that I checked that they study a lot and they say that there is nothing such formula. Although there are several estimates are done, but the whole asymptotic expansion is known, but not the suitable existing what they need. So what was their first version result was that for nu is for a real number greater or equal to 2, and for all x greater or equal to 1, we have this is of fx I nu x divided by phi x, which is square root of 2 pi x divided by e to the x, minus they truncate the series up to order 3, and the remainder they bound it by 5 nu to the 8 by 2x to the power 4 for all x greater or equal to 1, which was actually there for their purposes. But they had to appear a second version, which was appeared in the final version in the paper in 2020-21. So they appeared for all nu greater or equal to 2 and for x not greater or equal to 1, but a function of v, which is 1 over 120 v to the 6 is a polynomial in v. Then we have this bound divided by 31 nu to the power 8 divided by 6 nu x to the power 4. So they bound this thing by a constant times nu to the 8, which is a parameter dependent on the function, and the next higher order term x to the power 4. But the question is that I was first intrigued by the result that I thought myself that whether I couldn't prove or I can prove for all x greater or equal to 1, because I also need that in context of cubic partitions. But I thought I do not know whether I could prove. But when their result appeared, I checked numerically several times for several v, for several x, so that this actually holds. And this actually holds. But in the proof, there is subtle changes has to be made, and they made these changes and when the final version come. But it's now no longer x greater or equal to 1. So in order to prove any theorem, they had to rely on the computer or in a computer algebra program that they had to check for 1 to nu to the power 6. So nu gets higher and higher. They had to check lot more and more terms when they do this estimation for x greater or equal to some function of v. But this actually motivated me to prove their result for the first version. So in order to proceed for the proof, here I will describe in short that how I could prove, and I want to get in terms instead of 3 I get n, so as to get a function of some nu to the power some 2n plus 2 divided by x to the power n plus 1. So throughout the rest of the talk, I'll define for a is a real number. So a falling factorial to be this product a times a minus 1 times up to a minus k plus 1, and k for 0 is equal to 1. A rising factorial of is defined to be a times a plus 1 up to a plus k minus 1, and for k equal to 0 is 1, and then consequently binomial h of m, a falling factorial m divided by m factorial, and the gamma function as I already defined, but I defined for t is strictly greater than 0 real number, and the two incomplete gamma functions are there from 0 to s and s to infinity. So if I add these two gamma functions, incomplete gamma functions, I get the gamma function gamma t. So now I trace back to the asymptotics, how this asymptotic study has been began. So I saw that fx to be I nu of x. My goal is to find that how phi x and psi x can be found in this form. So psi x has to be in this form from 0 to infinity am divided by chi x to the power m. Due to Jacques Hadamard, what I found on the Watson's book on the treatise of element on the Bessel function, the monumental work of Watson, for nu belongs to real numbers strictly greater than minus half, which is enough for my purpose. So I nu of x defined by this integral representation. x over 2 to the power nu, gamma nu plus half times gamma half, 0 to pi to the x cos theta, sine to the power 2 nu, sine theta to the power 2 nu d theta. Now, as we have already seen in the graph, that these Bessel functions, modified Bessel functions of growth is like exponentially, so as is indicated by these encoded in this e to the power x cos theta. So our goal is to extract this e to the x first. So I extract e to the x so as to adjust minus x times 1 minus cos theta. And then I replace the sine theta over 2 to be u. And then I transform this integral to this integral 0 to 1 e to the minus 2 u square x e to the power 2 u to the power 2 u, and this 1 minus u square to the power nu minus half d. Now, since u is sine theta by 2, so mod u is less than 1, and I can say that I can expand in a power series, infinite power series, convergent m from 0 to infinity, nu minus half binomial m minus u square to the power m, and swap the integral and the sum so as to get in the formula nu minus half binomial m minus 1 to the m, and the rest 0 to 1 e to the power minus 2 nu square u square x and u to the power 2 nu plus 2m du. And finally, if I replace 2u square x to be t, then I get this expression e to the x divided by square root of 2 pi x times m from 0 to infinity, nu minus half binomial m minus 1 to the m, this is a constant, by 2 to the m x to the m, gamma nu plus half, and this integral. Now the question is, how could I get the asymptotics of that? So I'll trick with this integral, so 0 to 2x from 0 to infinity minus 2x to infinity. And then this 0 to 2 infinity, I have a closed form, this gamma nu plus m plus half. And gamma nu plus m plus half divided by gamma nu plus half is just nu plus half rising factorial m. And I take this factor on the other side, and the rest is my error term. So it's enough to check as x tends to infinity, this incomplete gamma function goes to e to the power minus 2x to the power nu minus half. And if I say again x tends to infinity, this goes to 0. This means that this left hand side is at the square root of 2 pi x over e to the x times I nu x, actually x tends to infinity goes to this form, sum m from 0 to infinity. This is my am divided by 2 to the m divided by x to the power m, this form. So I nu x, consequently I get e to the x divided by square root of 2 pi x m from 0 to infinity am nu by x to the m. So where am nu is minus 1 to the m nu minus half binomial m times nu plus half rising factorial m divided by 2 to the m. So now our goal is to extract this infinite expression in this psi n x, as we have discussed in the beginning, the refine n from infinity to a finite n, so that we want to estimate this factor to be e nu nx. So this error term is dependent on nu and this cutoff point n, and we want to get for all x greater or equal to 1. So how could I estimate this thing? So I first again go back to the definition, that square root of 2 pi x divided by e to the x I nu x. The right hand side is an infinite series, and then I extract this infinite series as usual, m from 0 to n and n plus 1 to infinity. So but still from m from 0 to n, I do not get the exact expression as I got in the psi x formula here. So I again do this trick, that 0 to 2x to 0 to infinity minus 2x to infinity. In the resultant, that e nu x is actually from minus m from 0 to n, this factor 2x to infinity, plus m from n plus 1 to infinity, 0 to 2x of this incomplete factor. But the question is that now I want to estimate the absolute value of this e nu n of x, but I had to consider based on this parameter nu and this n cutoff point. Why? Because this nu minus half binomial m, this behaves completely differently when nu is either greater than m or nu is less or equal to m. So based on this, I split this when nu is strictly greater than n. I split this in this fashion, minus m from 0 to n. I retain the first sum and split this n plus 1 to infinity to n plus 1 to nu and nu plus 1 to infinity, these two sums. For the other factor, I just retain as it is, because m from 0 to n and n plus 1 to infinity for sum 4 and sum 5. So now I will first state what is my structure to prove nu strictly greater than n, and what is my structure for the proof nu is less or equal to n. So for nu strictly greater than n, if I see all of this series, so if I take this sum and swapping this integral and the sum, then I can see that this nu minus half binomial m times this minus 1 to the power m, and this t to the power m is there. So if I replace here, t divided by 2x to the power m is there. So I'll see that for alpha is a positive real number strictly greater than 1, and nu is a positive integer greater or equal to 2, and n is a positive non-negative integer with the condition that nu is strictly greater than n. Then one can prove this is alternating, this sum is alternating. That means minus 1 to the power n, if I defined by this prefactor, and then sum m from 0 to n, nu minus half binomial m minus 1 alpha to the power m strictly greater than 0. And the idea of the proof of this lemma, so if I see this as a polynomial in alpha, p of alpha, if I define this as a polynomial in alpha, p of alpha, I want to express this polynomial p of alpha in terms of p of alpha minus 1. So it's written in terms of alpha, I want to express in terms of alpha minus 1. And then one can get directly that this expression is positive. But for the second thing, which I need in order to estimate for all alpha within the interval open 0 and closed 1 with nu strictly greater than n, then minus 1 to the power n, this is again alternating but with opposite fashion, this strictly less than 0, n plus 1 to nu. But here I had to rely on the induction principle and on the transition of the from inductive step to inductive hypothesis, and then the final thing, I want to get a recurrence. And for the recurrence, I had to I used the computer algebra package by Professor Peter Paule and Michael Schorn, that RISC fast Dale package based on the Zeilberger's algorithm. So how one would prove this thing further? So I defined this e nu n1x because here I consider nu to be strictly greater than n. So that is why I take nu in the superscript and n in the subscript. So this is defined to be minus this first sum m from 0 to n, and this 2x to infinity to the minus dt to the nu plus m minus half dt. And then I swap, and then I write this sum in this form m from 0 to n, nu minus half to binomial m minus theta to the power m, where theta is t divided by 2x. And as t goes from 2x to infinity, so theta is strictly greater than 1. So therefore, using this estimation, this alpha is my t by theta now. So using this estimation, we can prove that this e nu n1 of x is bounded by this factor divided by gamma nu plus half 2x to the power n plus 1, and this incomplete gamma function of nu plus n plus 3 over 2 by 2x. Similarly, for the second factor, for the sum 2, I can get this is t divided by 2x. Here theta is less or equal to 1. So this can be bounded by the same factor in the numerator and the denominator times another incomplete gamma function, gamma nu plus n plus 3 over 2 times 2x. So if I add them to, this would be gamma nu plus 3 over n plus 3 over 2 divided by gamma nu plus half, which is nu plus half rising factorial n plus 1. But there's another factor that for the third sum, if I trace back to this sum, the third sum, this is an infinite sum. Now there is no alternating sign pattern is there. So either it is always positive depending on nu or always negative. So if I take the absolute value, we first have to understand this integral sign. And the integral sign we want to understand it by the integrand explicitly. So what is the integrand of the form? The integrand of the form is e to the minus x times x to the y. And we saw that we proved this inequality for all x, y, for both are non-negative real numbers, strictly positive real numbers, sorry. E to the minus x times x to the y is strictly less than 1 over square root of 2 pi times gamma y times square root of y. And the proof strategy is that if I see this is a function of x, then if I differentiate, I will see that maximum at x equal to y. Then if we see that the maximum of this function is e to the power minus y times y to the y, and by Stirling's asymptotics formula, using the inequality, we can get that 1 over square root of 2 pi times gamma y times square root of y. Now, using the above inequality, we can estimate the last sum, the third sum, by these two factors. I'm not going into the details, nu greater or equal to n plus 2 for nu equal to n plus 1, these two factors. And these bounds are optimal. That means we can bound it, we can make a lower bound of this fashion, in this form. So this is the first part for nu strictly greater than n. And for nu less or equal to n, so for finally, we get this 1 plus e nu of n plus 2 and e nu of n plus 1 for the final form. So e nu nx for nu strictly greater than n in script nu subscript n of, and then the absolute value of this a n plus 1 nu, which I defined earlier, which is something v plus v minus half binomial n plus 1 times v plus half binomial, rising factorial n plus 1 divided by 2 to the power n plus 1. So we do not have to recall these formulas, but let for nu less or equal to n. So for nu less or equal to n, we first swap the sum and want to analyze this sum, this nu minus half binomial n minus 1 minus theta to the power nu. And the same scenario happens here, that m from 0 to n, nu minus half binomial m minus theta to the power m. Then we write this sum. This is a p theta. If I write again the same strategy, p theta, then we want to express in terms of theta minus 1. Now, these transformations helps to understand what is this sum actually behaves like, because we know this sum very well, because this 1 over 2m minus 2 nu plus 1, if we ignore that for m from 0 to nu, this is negative, nu minus 1, for nu is positive, and from nu plus 1 to n it's positive. So it's asymptotics to this sum m from 0 to n, 1 over 2m plus 2, roughly in binomial n choose n, theta minus 1 to the n. This is nothing but nu minus half binomial n plus 1 times this sum of theta to the power I running from 0 to n. So if we expand using this expression, then we got this en of nu plus nu 1 of x, the first fact for the fourth sum for nu less or equal to n, bounded by this constant. So now this is the extra expression we obtain. You see that this is square root of n log n appears extra. And again, we can prove that this is optimal, because when we take this x to be n by 2, then we can find that it actually happens that at that point, the square root of n log n, this discrepancy appears only at that point. Otherwise, it's completely under control in this fashion. And en nu 1 to be 1 by square root of 2 pi times this 1 over log n plus something constant by 1 over n of 2. And for the last thing, it's again, one can do in the similar fashion as for nu strictly greater than n to bound by square root of n. So all together, we can bound this for nu less or equal to n, e nu n of x of some prefactor e n nu times a n plus 1 nu times x to the power n plus 1 times square root of n log n, where e n nu is given by this expression. So what we get all together for these two factors? So if I define a m nu to be this factor, nu minus half binomial n times nu plus half binomial rising factorial m by 2 to the n, then for all x greater or equal to 1, nu n, nu to be positive integer greater or equal to 0, non-negative, n to be a greater or equal to 1, then this is my fx 1 over phi x minus this truncation psi n of x, which is less than this constant. This cn is e nu n times absolute value of a n plus 1 nu divided by x to the power n plus 1, where e nu n is these factors depending on whether nu is greater or equal to n plus 2, nu equal to n plus 1, and nu less or equal to n. So if I place according to Brinkman, so for n equal to 3, so what I get for all nu greater or equal to 0, n equal to 3, and x greater or equal to 1, in Brinkman's fashion, we get e nu 3 absolute value of a 4 nu divided by x to the power 4. And if we see nu for greater or equal to 4, it's absolutely close to that, the actual thing, that nu to the power 8 divided by 382. The actual thing would be nu to the power 8 by 384. For nu equal to 3 and nu equal to 2, nu equal to 1 and nu equal to 0, we get a lot less, because these of the factors square root of n log n. This prevents to get to the 3 to the power 384. It's nu to the power 8 by 86, nu to the power 8 by 25, 12 nu to the power 8 by 5, and this one. So now, if we do understand these things in comparison to Brinkman, then we can get that yes, Brinkman's result is true. If I get this bound, that's nu to the power 8, or at least for nu to the power 8 by 25 by x to the power 4, which is obviously less than 5 over 2, 5 nu to the power 8 over 2 x to the power 4. And these inequalities actually help to understand that Brinkman asked for these, for this PKN, the sequence PKN, the k-colored partition for log concavity. But if I want to understand higher order log concavity, then we have to go further, not x cube, but up to further, maybe 6. For d equal to 4, we have to get more and more for n. We have to get n large and large enough. So then we want to need this type of inequalities that helps to understand the log concavity, that helps to answer or to understand the log concavity or higher order log concavity properties or Turing inequality properties of this type of sequences. And for half integral order, which I explained that for half integral order, nu is greater or equal to 2 and z greater or equal to 1, we see that I nu of order nu plus half is much more easier because we do not need such an detailed calculations for that in a sense, because if I see this expression e to the x divided by square root of 2 pi x, then if I replace nu to be nu plus half, then this is actually a binomial nu binomial m. Then m from 0 to infinity is no longer valid because m greater than nu is 0. So m from 0 to nu is there. And then if we see, it's much more simpler than the integral order. This can be bounded by this absolute value of the next term of the expansion of psi x is absolute value of an plus 1 times nu plus half divided by x to the power. So this is why I believe that Brinkman said that it is necessary to estimate the asymptotic expansion. Although the asymptotic expansion is known, such a formulation was not known in the literature. And it will be helpful to understand, to answer the questions like log concavity, higher order Turing properties of other sequences, partition functions for distinct partition into distinct parts, such sequences, or maybe several other, for k regular partitions, for Andrew's SPT functions. Yes, this was the objective of my talk. Thank you.
Thanks very much, Koustav, for a nice talk. Are there any questions? Okay, I have a couple of questions. So if you go to that result of Brinkman, Rollin, and Zach and others, so they have two versions, right? The one where you have one by one. Yeah.
Yes.
So it seems to me that there is some kind of a trade-off. Like if I look at the first version, I have on the right-hand side 2.5 times that thing, nu to the 8 upon x to the 4. And then in the below, it's like 5 point something times the same thing.
Yes.
But here on the first version, it's x greater than x in any r greater than or equal to 1, but here it has to be this 1 by 20. So, I mean, the bound is not better in the final version than in the previous. Am I wrong?
Yes.
Yeah.
Yes, actually, in the first version, there is a certain mistake was there in their calculation because they obtained an inequality based on the assumption that in a function or a parameter in the function, their inequality is true for the parameter involved in the function if the parameter is less than 1. Only then their inequality is true, but their inequality has to be true for all for the function has to be greater or equal to 2. It's depend on this nu. So it's a kind of DL. It's written in the DLMF, but it's condition subject to the inequality is true subject to the condition that the parameter is less than 1. But in this context, the parameter has to be greater or equal to 1. So that is why they had to change the version.
Oh, okay. And another question was, if you go a few slides back where you had this formula for D of n. Yeah, the one after this.
Yes.
Yeah, what is that notation? K congruent to L, I understood, but what is that sub capital L? Below this, some 1 less than or equal to K less than or
yes, this is like that K is congruent to L mod capital L. I didn't incorporate into the every details because L is there.
So modulus is capital L. Yeah.
Yes.
Okay. Thanks. So, any other questions? If not, I would request everyone